A brass rod of length 50 cm and diameter 3 mm is joined to a steel rod of same length and diameter at the same temperature 40 degrees Celsius. Find the change in length of composite rod when heated to 250 degrees Celsius. The coefficients of linear expansion of brass and steel are 2 into 10 power minus 5 per degree centigrade and 1.2 into 10 power minus 5 per degree centigrade respectively. The ends of the composite rod are free to expand. Is there a thermal stress developed at the junction? So this is the question. So we are joining two rods which are equal in length and diameter. One is of brass and another one is of steel. Okay, and one they are joined to each other in like in a series, and the other two ends are free, and they have given the coefficients of linear expansion. Now they are asking us what is the change in the length of composite rod. That means the increase or decrease. The change can be increase or decrease, but here it is heated, so there will be an expansion. So what is that change? Okay, if initially there was some length, then if there was new length, what is the difference between those two lengths? That is what is being asked. And yes, let us see. So here we know for brass rod length is 50 centimeter and alpha is 2 into 10 power minus 5, and delta T is, what is delta T? Final temperature minus initial temperature, and it is 250 minus 40, that is 210 degrees Celsius. Therefore the increase in length, so I have already told you to remember, please, delta L is equals to L alpha delta T, where L is the initial length and alpha is the coefficient of linear expansion, and delta T is the change in temperature. So on substituting the values, we get 0.21 centimeters. So what is this? This is the change in length for brass rod. Similarly, what is the change in length of steel rod? You have to substitute the values for alpha, L and delta T for the steel rod. Value of alpha is different for steel rod, so just substitute it and the answer you are getting is 0.13 centimeter. So yes, their ends are free to expand, only one of their ends are joined to each other, so the total increase in length will be the addition of these two, 0.21 plus 0.13, that is 0.34 centimeter. So this is the change in length. No thermal stress is developed at the junction since the rod is free to expand. Yes. So as the rods are free to expand at the two ends, so there will not be any stress developed. The coefficient of volume expansion of glycerin is 49 into 10 power minus 5 per degree centigrade. Find the fractional change in its density for a 30 degrees Celsius rise in temperature. So there uh, we are given the change in temperature as 30-degree rise, and the gamma is 49 into 10 power minus 5 per degree centigrade. So now we want to find fractional change. Fractional change is nothing but it is change in the value by the initial value. Here it is like change in density by initial density, that is delta rho by rho initial. So that is what is called as fractional change. So now we know the formula, that is rho dash, that is final density equals to rho into, that is initial density into 1 minus gamma delta T. Now rho dash by rho equals to 1 by 1 minus gamma delta T, and that we can substitute the values of gamma and delta T. Okay, so that we are getting this value rho dash by rho as 1 minus 0.0147. But we know one more thing, so please see this one. Bring this 0.0147 to the left side and take this to the right side. Okay, then we get 1 minus rho dash by rho, that is equals to 0.0147. So what does this indicate? This indicates rho minus rho dash by rho, that is rho minus rho dash by rho. What does it mean? The change in the value by the initial value. So that is what is nothing but fractional change. So we get the answer directly. A 10 kilowatt drilling machine is used to drill a bore in a small aluminium block of mass 8 kilogram. How much is the rise in temperature of block in 2.5 minutes? Assuming that 50% of power is lost in the heating the machine to the surroundings. The specific heat of aluminium is 0.91 joule per gram per degree centigrade. So here we use a 10 kilowatt drilling machine to drill a bore in an aluminium block. The mass of that aluminium block is 8 kilogram, and they are asking us what is the rise in temperature of that aluminium block. Okay, and the time given is 2.5 minutes, and it is also said that 50% of the energy is lost in heating and to the surroundings. So yes, we can see the answer. So the power that is given is 10 into 10 power 3 watts, that is 10 kilowatt, that is 10 power 4 watt, and mass of the aluminium block is 8 kilogram. And because of the drilling, there is a rise in temperature of that aluminium block. Okay, and that rise in temperature is what is being asked, and the time is given as 2.5 minutes. Okay, and they are asking us to find the change in temperature of the block in that minutes, that time only. So we are taking that 2.5 minutes and 2.5 into 60 seconds, so we can convert minutes to seconds. Now 50% of the power is lost, so that is given in the question. And what is C? That is specific heat of aluminium, that is specific heat of that aluminium block, that is 0.91 joule per gram per degree centigrade. Now from the values of power and time, we can calculate the value of energy. So energy is nothing but power into time. Here it is energy dissipated. Okay, it is 10 power 4, that is power, into time is 2.5 into 60, that is 1.5 into 10 power 6 joules. Now from this, so 50% is lost, only remaining 50% is useful. We have already seen that. So out of the energy, total energy, only 50% is useful and 50% is lost. So now we want to find the useful energy. So what is the useful energy? That is 1.5 into 10 power 6 joule into 1 by 2. So that is what is the useful energy. So yes, what is the answer? It is 7.5 into 10 power 5 joules. And the 50% of energy which was useful, that is used to increase the temperature of that aluminium block. Okay, so what was the energy that was dissipated? That is dissipated, and the remaining energy is used in increasing the temperature of that block. So we can use Q equals to mc delta T. So what is the Q? It is half of the energy, that is 7.5 into 10 power 5. That is equals to, what is the mass? It is 8 kilograms. C is 0.91 into 10 power 3. Here we are converting it into joule per kilogram per degree centigrade, because 8 we have taken it in kilogram. Okay, so we have to convert this as also in kilogram into delta T. So from this, on substituting the values, we can get the delta T, that is equals to 103 degrees Celsius. A copper block of mass 2.5 kilogram is heated into a furnace to a temperature of 500 degrees Celsius and then placed on a large ice block. What is the maximum amount of ice that can melt? Uh, there are given values: specific heat of copper and heat of fusion of water. So here we have a copper block of mass 2.5 kilogram, and we are heating it up to 500 degrees Celsius. Now we are keeping that copper block on the ice block. Okay, now the question is what amount of ice is melting, and that is the question, we have to find it. So there are given two values: specific heat of copper is given and heat of fusion of water, that is for melting. What is the value of L? That is latent heat, that is given. Now let us see the answer. So this is the mass of copper, that is 2.5 kilogram. Temperature is 500 degrees Celsius, that is of copper, and C is 0.39, that is specific heat of copper is 0.39 joule per gram per degree centigrade. And for ice, we have to find the what is the mass of the ice that is melted, that is m dash, and latent heat is given as 335 joule per gram. Okay, now let us see the answer. And what will be the temperature of ice? That is 0 degrees Celsius. Okay, now Q is equals to heat taken by the block, mc delta T. So heat required for the melting of ice is provided by the copper, because copper was at higher temperature. So what is the energy here is going to be taken? That is mc delta T. So we have to consider for copper. Okay, so this is the heat given out by the copper. Okay, please try to understand, this is the heat given out by the copper, and this will be taken by the ice. Okay, and this heat is enough to melt some amount of ice, and we have to find that amount of ice. So now what is the heat given out by the copper block? That is mc delta t. So use the values for copper. It is 2.5 into c, 0.39 into 10 power 3, because we are converting into kilograms. Okay, per gram is converted into per kilogram. That is the reason. Into what is delta t? So the temperature will be falling to 0 degrees Celsius. So it is 500. 500 minus 0. So it is 500 only. So this is the value of Q. Now we know Q equals to ml, because this heat energy is going to be taken by the ice in order to melt. So the some amount of mass is melted, and that mass is m dash. So now m dash is equals to q by L. Just substitute the values of q and L. So you are going to get the answer 1.455 kilogram. So this is the amount of ice that is melted. In an experiment on the specific heat of a metal, a 0.2 kilogram block of metal at 150 degrees Celsius is dropped in a copper calorimeter of water equivalent 0.025 kilogram containing 150 centimeter cube of water at 27 degrees Celsius. The final temperature is 40 degrees Celsius. Compute the specific heat of metal. Density of water is 10 cube kilogram per meter cube, and specific heat is 4.2 into 10 power 3 joule per kilogram per degree centigrade. If heat losses due to the surroundings are not negligible, what is your answer? Greater or smaller than the actual value of the specific heat of the metal. So now please listen to the question. We have a metal, that is we have to find the specific heat of the metal. So this 0.2 kilogram of this metal, which is at higher temperature 150 degrees Celsius, is dropped into the calorimeter, and the calorimeter, that is water equivalent of the calorimeter is 0.025 kilogram. Let us see how we are using that water equivalent. And the water in the calorimeter, the volume of water is 150 centimeter cube of volume. So we have to convert it into mass, because in the formula we use the mass. And the calorimeter and water both are at the temperature 27 degrees Celsius, and the specific heat of water is 4.2 into 10 power 3 joule per kilogram per degree Celsius. Now we are going to use the mass in the formula. So we have to find the mass using this density and volume. So mass is equals to density into volume. Density is 10 cube kilogram per meter cube. Volume is 150, and this is centimeter cube. So centimeter cube we have to convert it into meter cube. So it is 10 power minus 6 meter cube. So the answer is 150 into 10 power minus 3 kilogram. So this is the mass of the water. Okay, the mass of the water is this much. Water equivalent of calorimeter is this much. Now we know one thing. Yes, it is also given the final temperature. So after dropping the metal in the calorimeter, which is having some amount of water, the final temperature of the things comes out to be 40 degrees Celsius. Now the question asks this: what is the specific heat of the metal? We know one thing. Heat lost by the metal is what is the heat taken by the calorimeter and water. So we have already seen this. Now what will be the heat lost by the metal? So we have to use the values for metal. It is mc delta T. Now as I have already told you, here the delta T, you can remember, it is like higher temperature minus lower temperature for that particular body. And what is the mass of the metal? It is 0.2 kilogram. C, we have to find the value of C. Here delta T is what is the initial temperature of the metal? That is 150 degrees Celsius. The final temperature comes out to be 40 degrees Celsius. So higher minus lower, it is 150 minus 40. So please take like that way. That is equals to 22C. Now this heat is lost by the metal, and this heat is also taken by the calorimeter and water. Now if we have the mass of the calorimeter separately, and we have the value of C for calorimeter separately, then we are not going to take it like this. Actually we will take like mc delta T plus mc delta T. So mc delta T of calorimeter will be taken in one side, and mc delta T of water will be taken, and they will be added together. But here they are giving the water equivalent. So this is how we use the water equivalent. That is mc C delta T. So here we are going to add the masses and we are going to use the C which is for water only. Okay, so that is the difference. So please try to catch the difference. If we have the mass of calorimeter and what is the specific heat of calorimeter separately, then we may not use like this. Then we will not use the formula in this way. We will use mc delta T for calorimeter plus mc delta T for water. Okay, but here as the water equivalent is given, we are just adding the masses. This mass and this mass we are adding together, and we are taking the specific heat of water and we are taking the change in temperature. Okay, and in that case it will be simple. Here you have to note how to use, that is enough. And on adding this 2 we get 0.175 and C is 4.2 into 10 cube and delta T. What is delta T? The initial temperature of water is 27 degrees Celsius, and as it is gaining the heat from the metal, its temperature will be raised and the final temperature is 40 degrees Celsius. Again take higher minus lower, it is 40 minus 27, that is 13. So the answer is 9555 joule. So now we can equate these two things because heat lost by the metal is equals to the heat taken by the calorimeter and water. So we can equate these two. 22C equals to 9555. So from this we get the value of C as 434.3 joule per kilogram per degree centigrade.